Welcome to Sleepless Astronomer, where we explore the wonders of space and the universe. If you're enjoying these cosmic journeys, please like this video and subscribe to the channel. We post new videos every single day, so you can tune in whenever you want to learn about the cosmos. And we'd love to hear from you in the comments. Let us know where in the world you're watching from. We always enjoy connecting with fellow space enthusiasts around the globe. Now let's begin tonight's journey through the universe. The powerful magnetic fields of dead stars. When a massive star exhausts its nuclear fuel and explodes as a supernova, the collapsing core is compressed into an object of almost incomprehensible density. A neutron star, containing more mass than the Sun, packed into a sphere only about 20 kilometers across. This violent compression doesn't just create extreme density, it also amplifies the star's magnetic field to strengths that dwarf anything found elsewhere in nature. The magnetic fields of neutron stars are among the strongest in the universe, billions or even trillions of times more powerful than Earth's magnetic field, strong enough to distort atoms, affect the fabric of empty space itself, and dominate the physics of everything near these stellar remnants. To understand how neutron stars develop such powerful magnetic fields, we need to consider what happens during the collapse. Before the supernova, the massive star had a magnetic field similar in strength to the Sun's, a few Gauss at the surface, comparable to a modest laboratory magnet. The star's magnetic field was generated by convection and rotation in its interior, creating currents of electrically conducting plasma that produced magnetism through the same basic dynamo process that generates Earth's magnetic field. When the star's core collapses, it shrinks from a radius of thousands of kilometers down to only about 10 or 12 kilometers, a compression factor of more than 1,000. As the core collapses, magnetic field lines are squeezed together. The strength of a magnetic field is proportional to the density of field lines passing through a given area, so compressing the core concentrates the field lines, amplifying the magnetic field strength enormously. The exact amplification depends on the details of the collapse, but conservation of magnetic flux, a fundamental principle stating that magnetic field lines cannot be created or destroyed, only moved around, requires that the field strength increase roughly in proportion to the decrease in the star's cross-sectional area. Shrinking the radius by a factor of 1,000 increases the magnetic field by about 1,000,000 times. A star with an initial field of 1 Gauss would emerge from collapse as a neutron star with a field of roughly 1,000,000 Gauss, or 1,000 Tesla. This is just the starting point. Most neutron stars have magnetic fields measured in hundreds of millions to trillions of Gauss. Earth's magnetic field, for comparison, measures about half a Gauss at the surface. The strongest continuous magnetic fields produced in laboratories reach around 45 Tesla, or about 500,000 Gauss, requiring enormous electromagnets and tremendous amounts of power. Yet neutron stars casually exceed these laboratory records by factors of millions or billions through nothing more than gravitational compression. Rotation adds another layer of complexity. The collapsing core spins faster as it shrinks, just as a figure skater spins faster when pulling their arms inward, another consequence of conservation of angular momentum. A star that initially rotated once every few weeks might emerge from collapse rotating several times per second, or even hundreds of times per second. This rapid rotation, combined with the intense magnetic field, creates the phenomenon we observe as pulsars. A pulsar is a rotating neutron star whose magnetic axis is tilted relative to its rotation axis, similar to how Earth's magnetic poles don't align perfectly with the geographic poles. Charged particles near the neutron star's surface are accelerated along the magnetic field lines toward the magnetic poles, where they emit beams of radio waves, X-rays, and sometimes even gamma rays. As the neutron star rotates, these beams sweep through space like lighthouse beams, When one of the beams happens to point toward Earth, we detect a pulse of radiation. The pulses arrive with extraordinary regularity. Some pulsars keep time more accurately than the best atomic clocks over short timescales. The Crab pulsar, formed in the supernova observed in the year 1054, rotates 30 times per second and has a magnetic field estimated at around 1 trillion Gauss. This field is strong enough to do remarkable things. If you could somehow place a human body in such a field, ignoring for the moment all the other ways a neutron star would kill you, the magnetic field would be strong enough to distort your atoms. The field would force electrons into different orbital configurations, changing the chemical properties of matter and making normal biological chemistry impossible. But some neutron stars have magnetic fields even more powerful than typical pulsars. These objects, called magnetars, possess the strongest magnetic fields known in the universe, reaching 10 to the 15th Gauss, or a billion Tesla. These fields are so strong that they affect empty space itself. According to quantum electrodynamics, the quantum field theory describing how light and matter interact, extremely strong magnetic fields can cause the vacuum to behave in strange ways. The vacuum can become birefringent, splitting light into two beams with different polarizations, similar to how certain crystals split light. Virtual particle pairs, electrons and positrons that normally pop briefly into existence and then annihilate, can be affected by the field, altering how light propagates through the vacuum. In magnetar fields, atoms are stretched into elongated shapes, becoming needle-like structures rather than the familiar spherical electron clouds. The magnetic field overwhelms the electric forces that normally determine atomic structure, forcing electrons into highly unusual quantum states. Matter at the surface of a magnetar exists in forms never encountered anywhere else, with properties unlike any material found on Earth or in laboratory experiments. Magnetars reveal their presence through sudden outbursts of X-rays and gamma rays. The magnetic field stores enormous amounts of energy. In the strongest magnetars, the magnetic energy exceeds the binding energy holding the neutron star together, creating immense internal stresses. The neutron star's crust, composed of crystallized nuclear matter, occasionally cracks under these stresses in events called starquakes. When the crust suddenly shifts, the magnetic field lines snap and reconnect violently, releasing tremendous bursts of energy in seconds or less. The most powerful magnetar flare ever observed occurred in December 2004 from a magnetar designated SGR 1806-20, located about 50,000 light-years from Earth. In 1/10 of a second, this flare released more energy than the Sun emits in 150,000 years. The radiation from this event saturated detectors on satellites throughout the solar system and measurably affected Earth's ionosphere, despite the enormous distance. If this magnetar had been located only 10 light-years from Earth instead of 50,000 light-years away, the flare would have caused a mass extinction, stripping away the ozone layer and exposing the surface to lethal radiation. The origin of magnetar fields remains somewhat mysterious. The simple compression of the collapsing star's field cannot account for fields this strong. Magnetar fields are hundreds to thousands of times stronger than what compression alone would produce. Several theories attempt to explain the enhancement. One possibility involves a dynamo mechanism operating in the first few seconds after the neutron star forms, when the core is still extremely hot and turbulent. Convection in the proto-neutron star, combined with rapid rotation, might amplify the magnetic field through a dynamo process, similar to how Earth generates its field, but operating under extreme conditions for a brief time. Another possibility involves the formation mechanism itself. If the collapsing core rotates very rapidly, near the maximum possible rate, differential rotation between the inner and outer parts of the core might stretch and amplify magnetic field lines, winding them up like a spring and creating the immensely powerful fields observed in magnetars. This would suggest that magnetars are born from progenitor stars that were rotating particularly rapidly before collapse, or from binary star systems where mass transfer spun up the star before the supernova. The magnetic fields of neutron stars gradually decay over time. The field energy is dissipated through various processes, including emission of electromagnetic radiation and heating of the neutron star's interior. Typical pulsars with fields around 1 trillion Gauss might maintain those field strengths for millions of years. Magnetar fields, being much stronger, decay more quickly, possibly over tens of thousands of years. As magnetars age and their fields weaken, they might become ordinary pulsars indistinguishable from neutron stars that never had magnetar strength fields. This decay helps explain why magnetars are relatively rare. Astronomers have identified only about 30 confirmed magnetars in our galaxy, compared to thousands of ordinary pulsars. If magnetar fields decay on timescales of 10,000 to 100,000 years, and they form perhaps once every few hundred years in our galaxy, then at any given time, only a few dozen active magnetars would exist, which matches observations well. The magnetic fields don't just affect the neutron star itself, they extend outward into space, creating a magnetosphere. Charged particles near the neutron star cannot cross magnetic field lines easily, so they become trapped, spiraling along the field lines. The field forces these particles to co-rotate with the neutron star out to a distance called the light cylinder, where the co-rotation velocity would equal the speed of light if the field could enforce it. Beyond the light cylinder, particles can escape along the field lines, carrying energy and angular momentum away from the neutron star. This energy loss causes pulsars to gradually slow down. The Crab pulsar's rotation period increases by about 38 nanoseconds per day, as it loses rotational energy to the magnetic field and the wind of particles it drives. The rate of slowdown reveals how much energy the pulsar is radiating. Young pulsars with strong magnetic fields slow down quickly. Old pulsars with weaker fields slow down more gradually. By measuring both the rotation period and the slowdown rate, astronomers can estimate a pulsar's age and magnetic field strength. Some of the fastest spinning pulsars, called millisecond pulsars because they rotate hundreds of times per second, have much weaker magnetic fields than typical pulsars. These objects were spun up to high speeds by accreting matter from a companion star in a binary system. The infalling matter transferred angular momentum to the neutron star, spinning it up, while simultaneously burying the magnetic field under a layer of accreted material, weakening the external field. These recycled pulsars have been rejuvenated by mass transfer, given a second life as rapidly spinning objects with relatively weak fields. The study of neutron star magnetic fields connects to fundamental physics in several ways. These fields exist at strengths where quantum electrodynamics predicts effects that cannot be tested in any laboratory. Observations of magnetars and the radiation they emit provide the only way to study matter and vacuum behavior in such extreme magnetic environments. The fields also affect how nuclear matter behaves at the neutron star surface and in the crust, influencing the equation of state, the relationship between pressure and density of matter at nuclear densities and beyond. Binary systems containing two neutron stars allow even more exotic magnetic interactions. When two magnetized neutron stars orbit close together, their magnetic fields can interact, possibly reconnecting and releasing energy. As the neutron stars spiral together, driven by gravitational wave emission, the magnetic fields might play a role in the final moments before merger, potentially affecting the gravitational wave signal and the electromagnetic radiation emitted during the kilonova that follows. The powerful magnetic fields of dead stars represent nature operating at extremes impossible to recreate artificially, fields where quantum effects modify the behavior of empty space, where atoms are distorted beyond recognition, and where enough energy is stored to power the sun for millennia, all concentrated in objects small enough to fit inside a city, yet massive enough to contain more matter than an entire star. Fields that define the physics of these remarkable objects and make them among the most extreme environments existing anywhere in the cosmos. The cosmic web that connects galaxies. When you look up at the night sky, the stars appear scattered across the darkness in what seems like a random pattern. Galaxies, those island universes containing billions of stars, seem to float in isolation, separated by vast gulfs of empty space. But zoom out far enough, pull back your perspective to encompass not just our galaxy or our local group of galaxies, but thousands, then millions, then billions of galaxies, and an extraordinary pattern emerges. The universe is not random at all. It's organized into a structure so vast and intricate that it resembles a three-dimensional spider's web stretching across the entire observable cosmos. This structure, called the cosmic web, represents the largest known organizational pattern in the universe. Picture it in your mind: long filaments of galaxies stretching across hundreds of millions of light years, connecting at massive nodes where galaxy clusters gather. Between these filaments lie enormous voids, regions of space so empty that they contain almost no galaxies at all. The filaments themselves are like highways of matter, channels along which gas flows and galaxies form, creating luminous threads that trace out the underlying architecture of space itself. The story of the cosmic web begins in the earliest moments after the Big Bang. In those first fractions of a second, the universe was nearly uniform, filled with hot plasma that was almost, but not quite, perfectly smooth. Tiny quantum fluctuations, variations in density that were only 1 part in 100,000, existed throughout this primordial material. These minuscule differences seemed insignificant, but they contained the seeds of everything that would come after. As the universe expanded and cooled, gravity began to amplify these tiny variations. Regions that were even slightly denser than average had slightly stronger gravity, which pulled in surrounding matter, making them denser still. This process fed on itself, with denser regions becoming denser over time, while less dense regions became emptier as their matter drained away toward the dense areas. But matter didn't just collapse into points, it collapsed along preferred directions, following the geometry dictated by the initial distribution of fluctuations. Imagine pouring cream into coffee and watching it swirl and fold into complex patterns before mixing completely. The early universe underwent something similar, but instead of mixing, the patterns froze into place, held there by gravity. Matter flowed along the paths of least resistance, streaming toward concentrations of mass, creating sheets and filaments rather than distributing itself uniformly. Dark matter played a crucial role in creating this web. This mysterious substance, which doesn't emit or absorb light but exerts gravitational force, makes up about 85% of all matter in the universe. Dark matter began clustering earlier than normal matter because it doesn't interact with light or other radiation. It formed a gravitational scaffolding, a framework of invisible mass and normal matter. The hydrogen and helium gas that would eventually form stars and galaxies fell into the gravitational wells created by this dark matter framework. The filaments of the cosmic web are not thin lines, but rather thick structures, typically about 20 to 30 million light years across, and stretching for hundreds of millions of light years in length. Along these filaments, galaxies form like beads on a string, though the string itself is made of dark matter with tendrils of gas threading through it. The gas in these filaments exists in a warm to hot state, typically between 100,000 and 10 million degrees, hot enough that it emits X-rays, but not dense enough to be easily observable. At the intersections where multiple filaments meet, enormous galaxy clusters form. These are the cities of the cosmic web, containing hundreds or even thousands of galaxies bound together by gravity. The largest galaxy clusters can contain as much mass as 1,000,000,000,000 suns, most of it in the form of dark matter, with substantial amounts of hot gas filling the space between galaxies. These clusters mark the nodes of the web, the places where matter has concentrated most densely. Between the filaments lie the cosmic voids, vast regions of space that are remarkably empty. A typical void might be 150 million light-years across and contain very few galaxies. These aren't completely empty. They still contain dark matter and some diffuse gas, but their density is only about 10 to 20% of the average density of the universe. Voids expand over time as matter continues to flow out of them toward the filaments and clusters, making them emptier with each passing billion years. The cosmic web reveals itself to astronomers through large-scale galaxy surveys. Telescopes map the positions of millions of galaxies, measuring not just where they appear in the sky, but also how far away they are. This three-dimensional mapping shows the web's structure clearly. Some of the most famous structures include the Sloan Great Wall, a concentration of galaxies stretching across 1.4 billion light-years, and the Hercules Corona Borealis Great Wall, which spans an almost incomprehensible 10 billion light-years. Our own Milky Way galaxy sits within this web, part of what's called the Local Group, a small collection of about 50 galaxies, including the Andromeda Galaxy and various smaller dwarf galaxies. This local group is located on the outskirts of the Virgo supercluster, a massive structure containing thousands of galaxies. Recent mapping has revealed that the Virgo supercluster is itself part of an even larger structure called Laniakea, a supercluster of superclusters spanning 520 million light-years and containing the mass of about 100,000 trillion suns. The gas flowing through the cosmic web carries matter from the voids into the filaments, and from the filaments into the galaxy clusters. This flow is not gentle. Gas moving through the filaments can reach speeds of several hundred kilometers per second, and when streams of gas collide at cluster locations, shock waves heat the gas to tremendous temperatures. These shock waves, called accretion shocks, occur at the boundaries of clusters where the web feeds new material into these gravitationally bound systems. Galaxies forming within the filaments have different characteristics than galaxies forming in the voids or clusters. Filament galaxies have better access to the gas supply flowing through the web, which allows them to continue forming stars for longer periods. Cluster galaxies, surrounded by hot gas and interacting frequently with other galaxies, often exhaust their star-forming fuel more quickly. Void galaxies, isolated and with limited gas supply, tend to be smaller and less luminous. The web is not static. It evolves over cosmic time as gravity continues to pull matter along its channels. Computer simulations of the universe's evolution show that the web was less pronounced in the early universe and has become more defined over billions of years. The voids have expanded. The filaments have thinned in some places while becoming more pronounced in others, and the galaxy clusters have grown larger as they consume matter from the surrounding web. Dark energy complicates this picture. This mysterious force which causes the universe's expansion to accelerate works against gravity's tendency to pull matter together. While gravity tries to make the web more concentrated, dark energy pushes space apart. The current era represents a transition. For the first several billion years after the Big Bang, gravity dominated and the web continued to grow more structured. But as dark energy's influence has grown stronger over time, it has begun to limit further structure growth. In the far future, dark energy will win, pulling the filaments apart and eventually isolating each galaxy cluster as an island in an ever-expanding sea of space. Scientists study the cosmic web using multiple techniques. Optical telescopes map the positions of galaxies. Radio telescopes detect the neutral hydrogen gas in and around galaxies. X-ray telescopes observe the hot gas in galaxy clusters and filaments. By combining these different views, astronomers build up a comprehensive picture of where matter exists and how it moves through the web's structure. The web also serves as a cosmic laboratory for studying dark matter. The way galaxies move within filaments and clusters, and the bending of light from distant objects as it passes through the web's mass concentrations, both provide information about the distribution of dark matter. These observations have helped confirm that dark matter exists, and have constrained theories about what dark matter might be, even though its fundamental nature remains one of physics' deepest mysteries. On the very largest scales, the cosmic web shows a surprising degree of uniformity. While the web has complex structure on scales up to a few 100 million light-years, if you average over regions a billion light-years or larger, the universe looks remarkably similar in all directions. This homogeneity on the largest scales supports the cosmological principle, the idea that on sufficiently large scales, the universe is essentially the same everywhere, with no preferred locations or directions. The web continues to influence galaxy evolution today. Our own galaxy, the Milky Way, is being pulled through space by the gravitational attraction of the web's structure. We're falling toward the Virgo cluster at about 400 kilometers per second, and at the same time, our entire local supercluster is being pulled toward an even more massive concentration of galaxies in the direction of the constellations Centaurus and Hydra, a region astronomers call the Great Attractor. Understanding the cosmic web means understanding how the universe transformed from a nearly smooth state shortly after the Big Bang into the rich, structured cosmos we see today. The web is a fossil record of the universe's history, preserving information about the initial conditions that existed billions of years ago, and documenting the ongoing battle between gravity, trying to pull matter together, and cosmic expansion, trying to spread it apart. Every galaxy in the night sky exists where it does because of this vast structure, this intricate architecture that connects everything in the universe into one enormous, evolving pattern. The incredible density of neutron stars. Imagine taking the entire mass of our Sun, a sphere so large that over 1 million Earths could fit inside it, and compressing it down to the size of a city. Not a large metropolitan area, sprawling across thousands of square miles, but just the central core, perhaps 12 or 15 miles across. This is a neutron star, an object so dense that a single teaspoonful of its material would weigh about 1 billion tons on Earth. To put that in perspective, that single teaspoon would weigh more than all the cars, trucks and buildings in a major city combined. This density is so extreme that it represents a fundamentally different state of matter, one that can only exist under the most extraordinary conditions in the universe. Neutron stars are born in the violent death throes of massive stars. When a star much larger than our Sun, typically at least 8 times more massive, exhausts the nuclear fuel in its core, it can no longer generate the heat and pressure needed to support itself against its own gravity. The core collapses catastrophically in less than a second, falling inward at speeds approaching 1/4 of the speed of light. The outer layers of the star, rebounding from this collapse, are blown away in a supernova explosion that briefly outshines an entire galaxy. What remains at the center, crushed under its own gravity to densities that boggle the mind, is a neutron star. To understand how neutron stars achieve such incredible density, you need to understand what happens to matter under extreme compression. In normal matter, atoms are mostly empty space. The nucleus of an atom containing protons and neutrons occupies only a tiny fraction of the atom's volume. The rest is empty space with a few electrons orbiting at relatively vast distances. In a solid object, like a piece of iron or a rock, the atoms are packed as closely together as the electromagnetic forces between them allow, but there's still enormous amounts of empty space within each atom. As you compress matter to higher and higher densities, you eventually overcome the forces that keep atoms intact. The electrons are stripped away from their nuclei, creating a plasma of free electrons and atomic nuclei. Compress further, and the electrons themselves are forced to occupy higher and higher energy states due to quantum mechanical principles. Eventually, at densities found in white dwarf stars, electron degeneracy pressure provides the support against gravity. The electrons can't be compressed any further without violating the Pauli exclusion principle, which forbids identical particles from occupying the same quantum state. But if you compress matter beyond even this point, as happens in the core collapse of a massive star, something remarkable occurs. The electrons are forced so close to the protons in atomic nuclei that they combine through a process called electron capture. A proton and an electron merge to form a neutron, releasing a neutrino in the process. This happens not just occasionally, but to nearly every proton in the collapsing core. Within a fraction of a second, the matter that was once composed of atoms, with protons, neutrons, and electrons maintaining their separate identities, transforms into a sea of neutrons, packed together so tightly that they're essentially touching. The neutrons themselves now provide the pressure that supports the star against further collapse. Just like electrons, neutrons obey the Pauli exclusion principle and cannot be compressed indefinitely. This neutron degeneracy pressure halts the collapse, but only after the matter has been compressed to densities comparable to that of an atomic nucleus. In fact, you can think of a neutron star as essentially a single gigantic atomic nucleus, several kilometers across, containing more neutrons than there are atoms in all the planets of our solar system combined. The density at the center of a neutron star is estimated to be around 500 million to perhaps a billion tons per cubic centimeter. At these densities, a cubic centimeter, about the size of a sugar cube, would contain more mass than Mount Everest. The entire mass of humanity, every person on Earth, could be compressed into a volume smaller than a grain of sand at neutron star densities. These numbers are so far beyond everyday experience that they almost lose meaning, but they represent real physical conditions that exist in these objects. The structure of a neutron star is complex and layered. At the surface, there's a thin atmosphere only a few centimeters thick, composed of hydrogen, helium, or heavier elements, depending on the star's history. Below this lies the outer crust, where matter exists in a crystalline lattice. Here, atomic nuclei, now incredibly neutron-rich and unlike any nuclei found on Earth, are arranged in a solid structure with a sea of electrons moving between them. This crust is extraordinarily rigid. It's been calculated that the material of a neutron star's crust is about 10 billion times stronger than steel. Deeper into the neutron star, at densities about 1 million times that of normal atomic nuclei, the inner crust begins. Here, neutrons start to leak out of the nuclei and form a superfluid that exists between and around the nuclei. A superfluid is a state of matter with zero viscosity. It flows without any resistance whatsoever. This neutron superfluid can exhibit bizarre quantum mechanical behavior on a macroscopic scale. Below the crust lies the outer core, where the density becomes so high that nuclei dissolve entirely into a uniform liquid of neutrons, with a small admixture of protons and electrons to maintain charge neutrality. The neutrons in this region form a superfluid, while the protons form a superconductor, a state where electrical current can flow without resistance. These quantum fluids make up the bulk of the neutron star's interior. At the very center, in the inner core, conditions become so extreme that we're not entirely certain what happens. The density may exceed that of atomic nuclei by a factor of several times. At these densities, neutrons themselves might break down into their constituent quarks, creating what's called a quark-gluon plasma, or strange quark matter. Alternatively, other exotic particles predicted by physics but never observed might appear. The center of a neutron star is one of the few places in the universe where matter exists in states that can't be recreated or studied in laboratories on Earth. The incredible density of neutron stars creates gravitational fields so strong that they noticeably warp space-time. At the surface of a neutron star, gravity is about 200 billion times stronger than on Earth. If you could somehow stand on a neutron star's surface, though you would instantly be crushed and vaporized, you would weigh 200 billion times more than you do on Earth. A fall from even a tiny height of 1 centimeter would be fatal, as you would hit the surface at a significant fraction of the speed of light. This intense gravity affects light itself. Photons climbing out of a neutron star's gravitational well lose energy through gravitational redshift. Light that starts as high-energy X-rays at the surface might emerge as lower-energy radiation by the time it escapes into space. The gravity also bends light rays, causing light from the far side of the neutron star to curve around and become visible to an observer. This means you could potentially see more than half of the neutron star's surface at once, as light from behind the star bends around it to reach your eyes. The intense gravity also means that space and time are severely warped near a neutron star. Clocks at the surface of a neutron star run about 30% slower than clocks far away in flat space-time. This time dilation is a real physical effect. Processes genuinely occur more slowly in the strong gravitational field at the surface compared to regions far from the star. The rotation of neutron stars adds another layer of extremes to their already extreme nature. Many neutron stars spin rapidly, some completing hundreds of rotations per second. This happens because of conservation of angular momentum. When the core of the parent star collapses, any rotation it had is amplified enormously as the radius shrinks. Just as a figure skater spins faster when pulling their arms in, a collapsing stellar core spins faster as it shrinks. The result can be a neutron star spinning so fast that its equator is moving at a significant fraction of the speed of light. The fastest spinning neutron star known rotates 716 times per second. Imagine an object with more mass than the Sun, compressed to the size of a city, spinning around more than 700 times every second. The surface at the equator of this neutron star is moving at about 24% of the speed of light. At these rotation rates, centrifugal forces become significant, causing the neutron star to bulge at the equator and flatten at the poles. Yet even with this rapid rotation and the outward force it creates, the neutron star holds together, a testament to the incredible strength of neutron degenerate matter and the overwhelming power of its gravity. The magnetic fields of neutron stars are among the strongest in the universe. The collapse that forms a neutron star compresses and amplifies any magnetic field present in the parent star's core. The result can be magnetic fields 1 trillion times stronger than Earth's magnetic field. Some neutron stars, called magnetars, have fields even stronger, up to 1,000 times more intense still. At these field strengths, quantum mechanical effects become important. The vacuum of space itself becomes polarized by the magnetic field, affecting how light propagates. Atoms stretched by these fields become elongated, many times longer than they are wide, fundamentally changing their properties. These magnetic fields, combined with rapid rotation, power some of the most energetic phenomena in the universe. Charged particles, accelerated along magnetic field lines, emit beams of radiation from the magnetic poles. If these beams sweep across Earth as the neutron star rotates, we detect regular pulses of radiation, which is why many neutron stars are called pulsars. The precision of these pulses rivals that of atomic clocks, with some pulsars maintaining their timing to within microseconds over years or decades. The density of neutron stars also means that they have very deep gravitational wells. The escape velocity from the surface of a typical neutron star is about 150,000 kilometers per second, roughly half the speed of light. This means that matter falling onto a neutron star from a companion star in a binary system releases tremendous amounts of energy. The infalling material accelerates to these extreme velocities and slams into the surface with incredible force, heating to temperatures of hundreds of millions of degrees and emitting intense X-rays and gamma rays. Neutron stars can also collide with each other in binary systems where two neutron stars spiral together due to the emission of gravitational waves. When they finally merge, the collision creates conditions even more extreme than those in individual neutron stars. The merger produces a burst of gravitational waves that ripple through space-time, along with electromagnetic radiation across the spectrum. These collisions are thought to be the primary source of heavy elements like gold and platinum in the universe, forged in the incredibly dense, hot material ejected during the merger. The study of neutron stars provides a unique laboratory for physics under extreme conditions. The densities, magnetic fields, rotation rates, and gravitational fields found in and around neutron stars simply don't exist anywhere else that we can observe. By studying these objects, physicists can test theories about how matter behaves at nuclear densities, how gravity warps spacetime in strong field regimes, and how quantum mechanics manifests on macroscopic scales. Every observation of a neutron star, every measurement of its mass, radius, rotation, or cooling rate provides constraints on fundamental physics that cannot be obtained any other way, offering glimpses into realms of matter and energy that push the very boundaries of our understanding. The extreme environments where life could thrive. Life on Earth exists in places that seem utterly hostile to survival. In boiling hot springs where water approaches its boiling point, in frozen Antarctic lakes where temperatures remain below zero year-round, in crushing depths of the ocean where pressure would flatten most organisms instantly, in intensely acidic pools that would dissolve metal, and in radioactive waste sites where radiation levels would kill a human in hours. These extreme environments, once thought to be sterile and lifeless, actually teem with organisms called extremophiles, life forms that not only survive but thrive in conditions that would destroy most familiar creatures. Understanding where these extremophiles live and how they manage to exist in such harsh conditions reveals that life's possibilities extend far beyond the comfortable, temperate zones we associate with habitability, suggesting that alien life might flourish in environments throughout the universe that we would never have considered searching. Temperature extremes represent one of the most dramatic challenges for life. At Yellowstone National Park and similar geothermal areas worldwide, hot springs reach temperatures near or even above the boiling point of water. In these scalding pools, organisms called thermophiles and hyperthermophiles thrive at temperatures that would cook most life forms. Some bacteria live comfortably at temperatures around 180 degrees Fahrenheit, and certain archaea, single-celled organisms distinct from bacteria, can survive and reproduce at temperatures exceeding 230 degrees Fahrenheit in superheated water under pressure that prevents it from boiling. These heat-loving organisms have specialized proteins that maintain their structure at high temperatures instead of denaturing and unfolding like normal proteins would. Their cell membranes contain special lipids that remain fluid and functional at temperatures where ordinary membranes would fall apart. Their DNA includes protective mechanisms that prevent the double helix from separating under thermal stress. Every aspect of their biochemistry has been optimized through evolution to function at temperatures that would destroy conventional life in seconds. The existence of thermophiles suggests that life could exist in hot environments throughout the solar system and beyond, in volcanic hot springs on Mars, in heated cracks near lava flows on Jupiter's moon Io, or in the scalding oceans of planets closer to their stars than Earth is to the Sun. At the opposite extreme, psychrophiles, cold-loving organisms, thrive at temperatures well below the freezing point of pure water. In Antarctica, microbes live in lakes that remain liquid beneath ice, because salt lowers the freezing point, maintaining temperatures around -5 to -20 degrees Fahrenheit. These organisms produce antifreeze proteins that prevent ice crystals from forming inside their cells, manufacture enzymes that remain flexible and functional at temperatures where normal enzymes become rigid and useless, and slow their metabolisms to conserve energy in the cold. Some bacteria found in permafrost remain viable after being frozen for hundreds of thousands of years, suggesting remarkable cold tolerance. The discovery of psychrophiles revolutionized thinking about where life could exist in the solar system. Europa, Jupiter's ice-covered moon, has a liquid ocean beneath miles of surface ice, kept liquid by tidal heating from Jupiter's gravity. The water at the bottom of this ocean, near Europa's rocky core, might be relatively warm, perhaps just above freezing, and could host psychrophilic life adapted to darkness and cold. Enceladus, Saturn's small moon, shoots geysers of liquid water through cracks in its ice shell, water that comes from a subsurface ocean. Despite the frigid surface temperature of -330 degrees Fahrenheit, the ocean beneath remains liquid, warmed by tidal forces. Life in these hidden oceans would need to tolerate extreme cold, total darkness, and high pressure, but Earth's psychrophiles prove that temperature alone doesn't preclude life. Pressure creates another extreme that life has conquered remarkably. In the Mariana Trench, the deepest part of Earth's oceans, pressure reaches about 16,000 pounds per square inch, more than 1,000 times atmospheric pressure at sea level. This crushing pressure would compress gases, alter protein structures, and collapse air-filled spaces in ordinary organisms. Yet the trench is inhabited by fish, amphipods, bacteria, and other creatures specifically adapted to extreme pressure. These organisms have no air-filled swim bladders that would collapse. Their proteins are stabilized by special amino acid sequences and by molecules called piezolites that counteract pressure's effects on molecular structure. Their cell membranes contain unsaturated fatty acids that remain fluid under pressure instead of becoming rigid. The existence of Barophil's pressure-loving organisms suggests that life could exist in the high-pressure environments found deep within planets and moons. The subsurface oceans of Europa and Enceladus experience significant pressure from the weight of overlying ice. The deeper regions of these oceans, near the rocky seafloor, would experience pressures far exceeding anything at Earth's surface. Yet if Earth organisms can adapt to pressures in the Mariana Trench, alien organisms might adapt to even higher pressures in alien oceans. Some scientists even speculate about life existing in the liquid metallic hydrogen regions deep within gas giants like Jupiter, though the extreme temperatures and pressures there would require biochemistry completely unlike anything on Earth. Acidity represents another extreme environment where life flourishes. Highly acidic environments with pH levels below 3, comparable to battery acid or stomach acid, would dissolve most biological molecules and disrupt normal cellular processes. Yet acidophiles thrive in such conditions. Iron Mountain in California hosts drainage from abandoned mines with pH levels below 0, more acidic than concentrated sulfuric acid. Despite this extreme acidity, bacteria and archaea live in these toxic streams, deriving energy from oxidizing iron and sulfur. These organisms maintain neutral pH inside their cells while existing in incredibly acidic environments, pumping protons out of their cells faster than the acidic environment can push them in, a process that requires substantial energy but allows survival in places nothing else can tolerate. At the opposite extreme, alkalophiles live in highly alkaline environments, with pH levels above 9 or even above 11. Soda lakes like Mono Lake in California and Lake Magadi in Kenya have pH levels around 10, nearly as caustic as bleach. Microorganisms in these lakes have adapted to maintain their internal chemistry despite the harsh external conditions, using specialized proteins and transport mechanisms to survive. The existence of life in both extremely acidic and extremely alkaline environments suggests that pH is a challenge life can overcome through evolution, expanding the range of potentially habitable environments to include caustic lakes and springs on other worlds. Salinity creates osmotic stress that would kill most organisms. Normal cells placed in very salty water lose water through osmosis and shrivel up. Yet halophiles, salt-loving organisms, thrive in hypersaline environments like the Dead Sea, where salt concentration exceeds 30%, and in salt evaporation ponds, where salt approaches saturation. Some archaea not only tolerate but require high salt concentrations to survive. They accumulate potassium and other ions inside their cells to balance the external salt concentration, preventing osmotic water loss. Their proteins are specifically adapted to function in high salt conditions and would actually denature and unfold in normal salt concentrations. Hypersaline environments might exist on Mars, where briny water could remain liquid at temperatures below the freezing point of pure water. Salts detected on Mars's surface could create localized regions where salty water exists seasonally or sporadically. If life ever existed on Mars, or if it exists there today, it might persist in these briny environments, sheltered from the planet's coal-thin atmosphere by adaptation similar to Earth's halophiles. Radiation represents one of the most challenging extremes. Ionizing radiation damages DNA, breaks apart molecules, and creates reactive free radicals that wreak havoc on cellular chemistry. Yet radio-resistant organisms can survive radiation doses thousands of times higher than would be lethal to humans. The bacterium Deinococcus radiodurans can withstand radiation exposure of several million rads, enough to shatter its DNA into hundreds of fragments and completely repair its genome within hours, reconstituting functional chromosomes from the pieces. This organism accumulates high concentrations of manganese compounds that protect its cellular machinery from radiation damage and possesses redundant copies of its genome, along with extraordinarily efficient DNA repair mechanisms. The discovery of radio-resistant life expands possibilities for life in high radiation environments throughout the universe. Mars's surface experiences high radiation levels because Mars lacks a strong magnetic field and thick atmosphere to shield the surface from cosmic rays and solar radiation. Any surface life on Mars would need radiation resistance. The moons of Jupiter, particularly Europa, exist within Jupiter's powerful radiation belts and experience intense radiation bombardment. Life in Europa's subsurface ocean would be shielded by miles of ice, but any organism near the surface would need extreme radiation tolerance. Desiccation, extreme dryness, challenges life by removing the water necessary for biochemical reactions. Yet xerophiles can survive in nearly waterless environments. Microorganisms have been found in the driest deserts on Earth, in salt crystals, and even in the upper atmosphere. Some organisms, like tardigrades, microscopic animals also called water bears, can enter a state called cryptobiosis when they dry out. In this state, they replace water in their cells with protective molecules like trehalose sugar, essentially turning into a glass-like solid that can survive for years or decades without water, then rehydrate and resume normal activity when water becomes available again. The ability to survive desiccation suggests that life could persist in extremely dry environments like Mars, where liquid water is rare and exists only transiently. Organisms in a cryptobiotic state could wait through long dry periods, potentially centuries or longer, then reactivate during brief periods when liquid water appears. This strategy might allow life to survive, even on worlds where habitable conditions are rare and sporadic rather than continuous. Oligotrophs thrive in nutrient-poor environments where most life would starve. These organisms can extract energy and nutrients from resources that seem impossibly limited. Some bacteria derive energy from oxidizing trace amounts of hydrogen gas or from reducing tiny concentrations of metal ions. Others grow incredibly slowly, dividing perhaps once per century or even less frequently, living at the absolute minimum energy budget that can sustain life. These organisms survive in deep subsurface rocks, in ultra-pure cave water, and in nutrient-depleted ocean regions. The existence of oligotrophs suggests that life could persist in environments throughout the universe that seem too resource-poor to support metabolism. Deep beneath the surfaces of planets and moons, in the pores between rock grains, organisms might eke out existence on trace amounts of hydrogen from water-rock reactions, or on the minimal nutrients leached from minerals over geological timescales. This greatly expands the potential volume of habitable space, not just surfaces and oceans, but the entire crustal volume of rocky worlds down to depths where temperature becomes prohibitive. Some of the most extreme environments on Earth combine multiple stresses. Hydrothermal vents on the ocean floor experience high temperature, high pressure, high concentrations of toxic metals and sulfur compounds, and complete darkness. Yet these vents support thriving ecosystems based on chemosynthetic bacteria that extract energy from chemicals spewing from the vents. Hot acidic springs combine high temperature with extremely low pH. Ice-covered Antarctic lakes combine extreme cold with high salinity and seasonal or permanent darkness. Life found in these multi-stress environments proves that organisms can adapt to simultaneous challenges, not just single extremes. This ability to tolerate multiple stresses simultaneously is crucial for evaluating habitability on alien worlds, where conditions often involve several challenges at once. Europa's ocean experiences cold, pressure, darkness, and possibly high salinity, all at the same time. Mars's surface experiences extreme cold, desiccation, high radiation, and low pressure simultaneously. Venus's clouds experience high acidity, moderate temperature, and the presence of sulfuric acid droplets. Each of these environments might seem impossibly hostile when considered as a whole, but examining them as combinations of specific stresses that Earth organisms have individually overcome makes them seem more potentially habitable. The extremophiles of Earth demonstrate that life is far more flexible and resilient than once thought. Organisms have evolved mechanisms to survive and thrive in virtually every environment on Earth where liquid water exists, at least transiently, and where some source of chemical energy is available. Temperature, pressure, acidity, salinity, radiation, desiccation, each extreme that seems to represent an absolute barrier to life, turns out to be merely another challenge that evolution can overcome, given time and the right selection pressures. These discoveries transform our search for life beyond Earth. Rather than looking only for planets with Earth-like conditions, moderate temperature, neutral pH, low radiation, abundant water, we can expand our search to include extreme environments throughout the solar system and beyond. Volcanic hot springs on Mars or Venus, frozen oceans on icy moons, the clouds of Venus, subsurface aquifers deep within asteroids, the hydrothermal systems that might exist beneath the surfaces of large moons. All of these become potential habitats once we recognize that life on Earth already thrives in analogous extremes. The extreme environments where life could thrive extend from the scalding vents of volcanic springs to the frozen lakes of Antarctica, from the crushing depths of ocean trenches to the desiccated rocks of the driest deserts, from intensely acidic mine drainage to alkaline soda lakes, from the radiation-blasted rocks near nuclear waste to the nutrient-depleted waters of remote caves. Each extreme habitat on Earth hosts specialized organisms that have turned hostile conditions into homes through remarkable biochemical and physiological adaptations, proving that life's potential territory extends far beyond the comfortable middle ground to encompass nearly anywhere liquid exists, energy flows, and raw materials can be found, vastly expanding the cosmic real estate where life might emerge and flourish across the universe. How we measure the weight of space objects. When astronomers announce that Jupiter has more than 300 times Earth's mass, or that a distant black hole contains several billion times the Sun's mass, these numbers might seem impossibly precise. How can we possibly weigh objects millions or billions of miles away, objects we can never visit or touch, objects that are sometimes completely invisible? The answer lies not in direct measurement, but in observing how these objects interact gravitationally with their surroundings. Mass reveals itself through gravity, and by watching how objects move under gravitational influence, astronomers can calculate masses with remarkable accuracy using principles that Isaac Newton worked out more than 300 years ago. The fundamental principle is simple. The more massive an object is, the stronger its gravitational pull, and the faster other objects must move to orbit it. This relationship, encoded in Newton's law of universal gravitation and his laws of motion, allows us to determine mass from orbital motion. If you know how fast something orbits and how far away it is from the object it's orbiting, you can calculate the central object's mass. For planets in our solar system, we measure their masses by observing their moons. Jupiter has dozens of moons, and each one's orbital period and distance from Jupiter reveals Jupiter's mass. The formula is straightforward in principle. The orbital period squared is proportional to the orbital distance cubed divided by the central mass. By measuring the period and distance, we can solve for the mass. The more massive the central object, the faster moons must orbit at a given distance to avoid falling inward. Jupiter's moon Io orbits very close to Jupiter and completes an orbit in only about 42 hours. Because Jupiter's immense mass creates powerful gravity, our moon takes 27 days to orbit Earth at a similar distance, because Earth is much less massive than Jupiter. For planets without moons, Mercury and Venus, determining mass required more ingenuity. Before the space age, astronomers studied how these planets affected each other's orbits through their gravitational interactions. When two planets pass relatively close to each other, their gravitational pulls slightly deflect each other's paths. By precisely measuring these tiny perturbations over years of observations, astronomers could infer the masses of the planets involved. Space probes visiting these planets provided much more accurate mass measurements by observing how the planet's gravity affected the spacecraft trajectories. Measuring Earth's mass required understanding gravity itself. In the late 18th century, British scientist Henry Cavendish performed a delicate experiment using a torsion balance, a horizontal bar suspended by a thin wire with lead spheres at each end. By bringing large lead masses near the suspended spheres and measuring like the tiny twist in the wire caused by gravitational attraction, Cavendish determined the strength of gravity between known masses. This measurement, combined with the known acceleration of gravity at Earth's surface, allowed calculation of Earth's mass. The experiment is sometimes described as weighing the Earth, though it really measured how strongly Earth's gravity pulls compared to the gravity between laboratory masses. For the Sun, measuring mass is straightforward because Earth and all other planets orbit it. Earth orbits the Sun at a distance of about 150 million kilometers with an orbital period of 1 year. Plugging these numbers into the orbital equation gives the Sun's mass about 2 times 10 to the 30th power kilograms, or about 330,000 times Earth's mass. The exact same calculation works for any star with planets. Measure the planet's orbital distance and period, and you can determine the star's mass. Binary star systems, 2 stars orbiting each other, provide mass measurements for individual stars. By watching the stars orbit their common center of mass and measuring their orbital periods, distances and velocities, astronomers can determine both stars' masses separately. This technique has measured thousands of stellar masses, revealing the relationship between a star's mass and its other properties, like luminosity and temperature. These measurements show that stars range from about 8% of the Sun's mass for the smallest red dwarfs up to perhaps 150 times the Sun's mass for the most massive stars. For more distant objects, techniques become more sophisticated but still rely on gravitational effects. Galaxies contain hundreds of billions of stars, and measuring a galaxy's mass means measuring how fast stars and gas orbit within it. By observing the rotation speeds at different distances from the galactic center and applying the same orbital principles, astronomers can calculate the total mass enclosed within each radius. This technique revealed the existence of dark matter. The rotation speeds in the outer parts of galaxies are far too high to be explained by the visible stars and gas alone, requiring the presence of large amounts of invisible mass. Galaxy clusters, groups of hundreds or thousands of galaxies, have their masses measured through multiple techniques. One method observes the motions of individual galaxies within the cluster. The galaxies orbit within the cluster's gravitational potential, and their velocities reveal the cluster's total mass. Another technique uses gravitational lensing, the bending of light from more distant galaxies by the cluster's gravity. The amount of bending depends on the cluster's mass, so by measuring how background galaxies appear distorted, astronomers can map the cluster's mass distribution, including dark matter. Black holes present special challenges because they are invisible and often have no nearby objects in simple orbits. For stellar mass black holes in binary systems, astronomers measure the orbital motion of the visible companion star. The star's velocity and orbital period reveal the black hole's mass, even though the black hole itself emits no light. This technique confirmed that several X-ray binary systems contain objects too massive to be neutron stars. They must be black holes. Supermassive black holes at galaxy centers are weighed by observing stars or gas orbiting near them. The Milky Way's central black hole, Sagittarius A star, has its mass measured precisely by tracking individual stars as they orbit. One star, designated S2, completes an orbit every 16 years in an elongated ellipse that brings it within about 120 times Earth's distance from the Sun, extremely close by galactic standards. By measuring S2's position and velocity throughout its orbit, astronomers calculated the black hole's mass at about 4 million times the Sun's mass. This measurement is accurate to within a few percent, despite the black hole being 26,000 light-years away. More distant supermassive black holes are measured through the motion of stars or gas closer to the black hole than telescopes can individually resolve. Instead, spectroscopy measures the range of velocities present in the light coming from the galaxy's central region. Broader velocity distributions indicate faster-moving material, which requires more mass to keep the material bound. Using this technique, astronomers have measured black hole masses ranging from millions to billions of solar masses in galaxies across the universe. Gravitational waves from merging black holes provide another mass measurement technique. When two black holes spiral together and merge, they emit gravitational waves, ripples in space-time itself, detected by observatories like LIGO. The frequency and amplitude of these waves encode information about the black hole's masses. The first gravitational wave detection in 2015 came from two black holes weighing about 29 and 36 solar masses that merged into a single black hole of about 62 solar masses, with 3 solar masses worth of energy radiated away as gravitational waves during the collision. For objects we can visit with spacecraft, mass measurements become more direct. The spacecraft's trajectory bends as it passes the object, with the deflection determined by the object's mass. By tracking the spacecraft's position using radio signals and measuring the Doppler shift in those signals, mission controllers determine the trajectory precisely. Comparing the observed trajectory to computer models reveals the mass that must have caused that particular deflection. This technique has measured masses of asteroids, comets, and moons with no satellites of their own. Small asteroids present particular challenges. Without satellites, and too small to significantly affect spacecraft at typical flyby distances, their masses remained uncertain until spacecraft flew very close or even orbited them. The near-Shoemaker spacecraft orbited asteroid Eros for a year, precisely measuring Eros's mass and density. The Hayabusa and OSIRIS-REx missions orbited small asteroids, Ryugu and Bennu respectively, measuring their masses through orbital mechanics and revealing that both asteroids are loose rubble piles rather than solid rocks. The precision of mass measurements varies enormously. The Sun's mass is known to about 7 significant figures. Earth's mass is known even more precisely because we can measure Earth's gravitational field from satellites in low orbit. Jupiter's mass is known very precisely from spacecraft tracking, but the mass of a distant galaxy might be uncertain by 10 or 20%, and masses of galaxy clusters can be uncertain by even more, particularly if dark matter doesn't follow the same distribution as visible matter. Understanding the limitations matters. When astronomers quote a mass, there's always uncertainty attached. Reporting that a black hole contains about 4 million solar masses acknowledges this uncertainty. The actual value might be 3.8 million or 4.2 million, and that range represents our measurement precision, not variability in the black hole's mass. All these techniques ultimately trace back to gravity, the fundamental force that governs how massive objects interact across space. Mass creates gravity, gravity creates motion, and by observing that motion precisely, we can work backward to determine the mass that caused it. From moons orbiting planets, to galaxies orbiting within clusters, from binary stars wheeling around each other, to stars orbiting supermassive black holes, the cosmos is filled with objects whose motions reveal the masses of the bodies that control them. By watching these cosmic dances and applying the mathematical laws that Newton first articulated, astronomers can weigh objects from the smallest asteroids to the largest galaxy clusters, measuring masses across a range spanning more than 20 orders of magnitude. From asteroids weighing billions of tons to galaxy clusters weighing millions of trillions of times more than the Sun, all without ever placing these objects on a scale, relying instead on the universal language of gravity that connects everything in the cosmos through the elegant mathematics of orbital motion. The thick atmospheres of Jupiter and Saturn. Jupiter and Saturn are fundamentally different from the rocky planets of the inner solar system. They have no solid surface to stand on, no ground beneath the sky. Instead, these gas giants are essentially enormous atmospheres all the way down, layers upon layers of gas that gradually transition from thin upper hazes to dense, crushing depths, where pressure transforms hydrogen into states of matter that don't exist naturally anywhere on Earth. Understanding these thick atmospheres means understanding worlds where the atmosphere isn't just a thin shell surrounding a planet, it is the planet. The atmospheres of Jupiter and Saturn are composed primarily of hydrogen and helium, the two lightest and most abundant elements in the universe. Jupiter's atmosphere is about 90% hydrogen and 10% helium by number of molecules, with trace amounts of methane, ammonia, water vapor, and other compounds making up less than 1%. Saturn has a similar composition, though with slightly less helium, about 96% hydrogen and 3% helium, with the missing helium thought to have settled deeper into the planet's interior over billions of years. This composition mirrors the composition of the Sun and the primordial solar nebula from which the planets formed, marking these giants as worlds that captured and retained their original atmospheres from the planet-forming disk. The visible clouds we see when we look at Jupiter and Saturn exist in the uppermost layers of these atmospheres, in a region where temperatures and pressures allow various compounds to condense into droplets and crystals. On Jupiter, the highest cloud layer consists of ammonia ice crystals forming at temperatures around -150 degrees Celsius, where ammonia gas freezes into white ice. These ammonia clouds give Jupiter's zones, the bright bands that circle the planet, their brilliant white appearance. Below this ammonia layer, at slightly higher temperatures and pressures, ammonium hydrosulfide forms another cloud deck, creating brown and tan colours. Deeper still, water ice and liquid water droplets form clouds, though these are rarely visible from above, hidden beneath the overlying layers. Saturn's cloud structure is similar but more subdued. The planet appears more uniformly golden tan because a high-altitude haze of unknown composition partially obscures the underlying cloud layers. This haze may consist of complex organic molecules called tholins, created when ultraviolet light from the sun breaks apart methane molecules in the upper atmosphere, allowing the fragments to recombine into larger, more complex hydrocarbons. These organic hazes absorb blue light and scatter red and yellow light, giving Saturn its characteristic buttery colour. The temperatures in these atmospheres change dramatically with depth. At the cloud tops, where pressure is similar to Earth's atmospheric pressure at sea level, temperatures on Jupiter hover around -145 degrees Celsius. On Saturn, they're even colder, around -180 degrees Celsius, because Saturn is nearly twice as far from the Sun and receives less solar heating. But as you descend into these atmospheres, temperatures rise rapidly. The increase comes partly from the Sun's heat that has been absorbed and transported downward, but more significantly from the planet's internal heat. Both Jupiter and Saturn emit more energy than they receive from the Sun. Jupiter radiates about 1.7 times as much energy as it absorbs from sunlight, while Saturn radiates about 1.8 times as much. This extra energy comes from the planet's interiors. Jupiter is still slowly contracting under its own gravity, a process that converts gravitational potential energy into heat through a mechanism called Kelvin-Helmholtz contraction, named after the physicists Lord Kelvin and Hermann von Helmholtz, who described this process in the 19th century. Saturn has an additional heat source. Helium is slowly separating from hydrogen in its interior and sinking toward the center, releasing gravitational energy as it falls. Much like rain falling through Earth's atmosphere releases energy. This internal heat drives powerful convection in the atmospheres. Warm gas rises from the depths, cools as it rises and expands, then sinks back down to be heated again. This convection creates enormous circulation cells that organize the atmospheres into the distinctive banded patterns visible on both planets. Rising gas forms the bright zones, where fresh ammonia ice crystals condense and create white clouds. Sinking gas forms the darker belts, where descending motion prevents cloud formation and allows us to see deeper into the atmosphere, where darker compounds and higher temperatures exist. The winds on Jupiter and Saturn are among the strongest in the solar system. Jupiter's equatorial region rotates faster than the rest of the planet, with winds reaching speeds of about 360 kilometers per hour, roughly 225 miles per hour. Saturn's equatorial winds are even more extreme, racing along at up to 1,800 kilometers per hour, over 1,100 miles per hour, making them the fastest planetary winds in the solar system. These winds are organized into jet streams, narrow bands of fast-flowing gas that separate the zones and belts. The jet streams are remarkably stable, maintaining their positions and speeds for decades or longer. The Great Red Spot on Jupiter is perhaps the most famous atmospheric feature in the solar system. This enormous storm, large enough to swallow 2 or 3 Earths, has been observed continuously since at least 1830, and possibly as far back as the 1660s, when early telescope observers noted a large spot on Jupiter. The storm is an anticyclone, rotating counterclockwise in Jupiter's southern hemisphere, with winds at its edges reaching 400 kilometers per hour. The storm's longevity remains somewhat mysterious. On Earth, hurricanes dissipate within days or weeks when they move over land or cooler water, but the Great Red Spot has persisted for centuries. Its stability likely comes from the fact that Jupiter has no solid surface to create friction and slow the winds, and the storm may draw energy from the smaller storms it absorbs, and from the temperature difference between the warm interior and cold upper atmosphere. Saturn hosts similar, but generally smaller and shorter-lived storms. Approximately once per Saturnian year, about every 30 Earth years, a massive storm erupts in Saturn's northern hemisphere, growing to encircle the entire planet before eventually dissipating. These great white spots, as they're called, were observed in 1876, 1903, 1933, 1960, 1990, and 2010, following a remarkably regular pattern tied to Saturn's seasons. The storms appear to originate when seasonal heating destabilizes the atmosphere, allowing deep, moist convection to punch through the stable layers above and create violent thunderstorms. Lightning occurs on both Jupiter and Saturn, detected by the Voyager, Galileo, and Cassini spacecraft through radio emissions, and in some cases visible flashes. The lightning on these worlds is similar to terrestrial lightning, electrical discharges between regions of different charge within clouds, but can be far more powerful than Earth's lightning. Individual lightning bolts on Saturn have been measured at up to 1 million times more powerful than typical lightning on Earth. These storms occur in the water cloud layer, where the same process that creates thunderstorms on Earth, rising moist air forming clouds and separating electrical charges, operates on these giant planets. As you descend deeper into these atmospheres, the pressure increases relentlessly. At depths of a few hundred kilometers below the cloud tops, pressures reach thousands of times Earth's atmospheric pressure, and temperatures climb to hundreds of degrees Celsius. The atmosphere becomes denser and denser, transitioning gradually from gas to liquid, though there's no sharp boundary, no ocean surface where you suddenly plunge from air into water. Instead, the hydrogen and helium gradually become so compressed that they take on liquid properties, while still being hot enough that calling them liquid doesn't quite capture their state. They exist in a supercritical fluid state, where the distinction between gas and liquid breaks down. Descend even deeper, to depths of 10,000 to 20,000 kilometers, and pressures reach millions of times Earth's atmospheric pressure. Under these extreme conditions, hydrogen transforms into metallic hydrogen, a state of matter where the atoms are squeezed so tightly that their electrons are freed from individual atoms and flow through the material like electrons in a metal. This metallic hydrogen is thought to make up the bulk of Jupiter's mass and a significant portion of Saturn's. It's an excellent electrical conductor, and the flow of metallic hydrogen in these regions, driven by the planet's rotation and internal convection, generates the powerful magnetic fields that both planets possess. The transition from molecular hydrogen to metallic hydrogen isn't abrupt. There's a gradual change over a range of depths where hydrogen takes on increasingly metallic properties. Scientists study this transition using laboratory experiments that compress hydrogen to extreme pressures and sophisticated computer simulations that model how atoms behave under conditions impossible to fully recreate on Earth. Understanding metallic hydrogen is crucial for understanding the interiors of Jupiter and Saturn, yet its properties remain uncertain because the pressures required, several million times atmospheric pressure, can only be achieved briefly in laboratory settings. At the very centers of Jupiter and Saturn, may lie rocky cores, though whether these cores exist and how large they might be remains debated. Jupiter might have a core of rock and ice, containing 10 to 20 Earth masses, or it might have no distinct core at all, just a gradual increase in the concentration of heavy elements toward the centre. Saturn might have a similar core, though perhaps smaller relative to the planet's total mass. NASA's Juno mission to Jupiter and the Cassini mission's final orbits, diving between Saturn and its rings, have provided gravity measurements precise enough to constrain the planet's interior structures, revealing that both planets have somewhat diffuse cores rather than sharp boundaries between core and envelope. The scale of these atmospheres is almost incomprehensible. On Earth, the atmosphere extends perhaps 100 kilometers before space begins. On Jupiter and Saturn, the atmosphere extends downward for thousands upon thousands of kilometers, transitioning through states from thin gas to dense supercritical fluid to liquid metallic hydrogen. If you could somehow survive the crushing pressures and searing temperatures and descend through Jupiter's atmosphere, it would take days or weeks of continuous falling to reach the planet's center, passing through layer after layer of hydrogen in different states, all of it technically atmosphere, because there's no solid surface to mark where the atmosphere ends. The study of Jupiter's and Saturn's atmospheres extends beyond academic interest. Understanding how these atmospheres work, how convection organizes into bands, how storms form and persist, how energy is transported from the interior to space, helps scientists understand atmospheric dynamics more broadly. The principles governing Jupiter's atmosphere apply, with appropriate modifications, to Saturn's atmosphere, to the atmospheres of Uranus and Neptune, and even to the atmospheres of giant exoplanets orbiting other stars. Some exoplanets, called hot Jupiters, orbit extremely close to their stars and have atmospheres heated to thousands of degrees, creating extreme versions of the processes we observe on Jupiter and Saturn. These thick atmospheres also serve as laboratories for studying hydrogen under extreme conditions. Most of the normal matter in the universe is hydrogen, and understanding how it behaves under high pressure is crucial for understanding not just giant planets, but also brown dwarfs, objects intermediate in mass between planets and stars, and the interiors of low-mass stars. The hydrogen in Jupiter and Saturn exists across a range of pressures and temperatures that spans from Earth-like conditions in the upper atmosphere to conditions approaching those in stellar interiors in the metallic hydrogen regions, providing natural experiments that inform our understanding of matter itself across a vast range of conditions. The lighthouse stars that spin incredibly fast. In 1967, a graduate student named Jocelyn Bell noticed something peculiar in her radio telescope delta, a signal that pulsed with extraordinary regularity, repeating every 1.3373 seconds. The precision was so remarkable that she and her advisor initially wondered whether they had detected an artificial signal from an extraterrestrial civilization. They jokingly called it LGM-1 for Little Green Men. But as more of these pulsing sources were discovered, each with its own precise period, it became clear they were witnessing something natural, but entirely unexpected: rapidly spinning neutron stars whose beams of radiation sweep across Earth like cosmic lighthouses. These objects, now called pulsars, are among the most extreme objects in the universe. They are neutron stars, the collapsed cores of massive stars that exploded as supernova, compressed to densities where a sugar cube-sized amount of material would weigh as much as a mountain. What makes pulsars special is not just their incredible density, but their rotation. These stars spin at rates that seem impossible for something so massive. Many complete one rotation in less than a second, some in mere milliseconds, whirling around hundreds of times per second while containing more mass than the Sun. The story of a pulsar begins with the death of a massive star. When a star, at least 8 times more massive than the Sun, exhausts its nuclear fuel, its core collapses catastrophically. The outer layers rebound and explode outward as a supernova, but the core continues collapsing until nuclear forces halt the compression, creating a neutron star about 12 miles across. This neutron star inherits the angular momentum of the original star's core, but because the radius has shrunk by a factor of perhaps 100,000, the rotation rate increases dramatically through conservation of angular momentum. Imagine a figure skater pulling their arms inward during a spin, rotating faster and faster as their radius decreases. The collapsing stellar core undergoes the same process, but on a far more extreme scale. A star that was rotating once every few weeks might produce a neutron star that rotates several times per second. The fastest spinning pulsar known, designated PSRJ 1748-2446 AD, rotates 716 times per second. At its equator, the surface is moving at approximately 70,000 miles per second, nearly 1/4 the speed of light. At these speeds, the neutron star is ablate, bulging significantly at its equator due to centrifugal forces, yet it holds together through the tremendous strength of neutron-degenerate matter and its own crushing gravity. The lighthouse effect that makes pulsars detectable comes from their magnetic fields. Neutron stars possess the strongest magnetic fields known in the universe, typically 1 trillion times stronger than Earth's magnetic field. When the core of the parent star collapses, any magnetic field present is compressed and amplified tremendously. This field doesn't simply shrink, it gets concentrated into a much smaller volume, intensifying to values that would tear apart atoms and polarize the vacuum of space itself. This intense magnetic field is not aligned with the neutron star's rotation axis. Just as Earth's magnetic poles don't coincide with its geographic poles, a neutron star's magnetic axis is typically tilted relative to its spin axis. Charged particles, primarily electrons and positrons, are accelerated along the magnetic field lines, particularly near the magnetic poles. These particles, accelerating at relativistic speeds, emit intense beams of radiation through a process called synchrotron radiation. The beams emerge from the magnetic poles, creating two searchlights that sweep through space as the neutron star rotates. When one of these beams sweeps across Earth, we detect a pulse of radio waves, X-rays, or gamma rays, depending on the pulsar's characteristics. The pulse arrives with extraordinary regularity. The best pulsars keep time as accurately as atomic clocks, varying by only microseconds over years. This precision exists because the neutron star is such a stable rotator. Its enormous rotational inertia, combined with its extreme density and rigidity, means that nothing can easily change its spin rate. It's like an enormous cosmic flywheel, storing vast amounts of rotational energy and releasing it only very gradually. The radio emission mechanism is complex and still not completely understood, despite decades of study. The acceleration of charged particles near the magnetic poles creates a cascade of electromagnetic radiation. These particles follow the curved magnetic field lines, and as they accelerate, they emit photons. These photons can interact with the intense magnetic field to create more particle-antiparticle pairs, which then accelerate and create more photons, building up a cascade that produces the intense radio emission we detect. The region where this occurs, just above the magnetic poles, is called the polar cap, and it's here that the lighthouse beams originate. Not all pulsars emit at the same wavelengths. Some are primarily radio pulsars, detected through their radio emission. Others are X-ray pulsars, emitting primarily high-energy X-rays. A few emit gamma rays, the most energetic form of electromagnetic radiation. Some pulsars emit across the entire electromagnetic spectrum simultaneously, creating pulses detectable from radio waves through gamma rays. The emission properties depend on factors like the neutron star's age, its magnetic field strength, its rotation rate, and the environment surrounding it. Young pulsars, recently formed in supernova explosions, tend to rotate faster and have stronger magnetic fields than old pulsars. The Crab pulsar, formed in a supernova observed by Chinese astronomers in 1054 AD, rotates 30 times per second and emits powerfully across the electromagnetic spectrum. It sits at the center of the Crab Nebula, the expanding remnant of that supernova explosion, and its intense radiation illuminates the surrounding nebula, causing it to glow. The pulsar acts like a cosmic power station, converting its rotational energy into electromagnetic radiation and high-energy particles that energize the nebula. Pulsars slow down over time, gradually losing rotational energy. This spin-down occurs because the rotating magnetic field acts like a brake. The magnetic field lines extend far into space, and as they rotate with the neutron star, they drag charged particles along, accelerating them and carrying away energy and angular momentum. This magnetic braking gradually robs the neutron star of its rotational energy. A young pulsar might slow down measurably over just a few years, while an old pulsar might take millions of years to show detectable changes in its period. The rate at which a pulsar slows down reveals information about its magnetic field strength and age. By measuring the current rotation period and the rate of change of that period, astronomers can estimate how long the pulsar has been spinning down and how much longer it will continue to pulse before its rotation becomes too slow and its magnetic field too weak to generate detectable radiation. Most pulsars have lifetimes of tens of millions of years as active radio sources before they fade from detectability, though the neutron star itself continues existing and spinning, just no longer producing observable pulses. Some pulsars experience sudden speed-ups, called glitches. The neutron star's rotation rate, which normally decreases steadily, suddenly increases slightly, then resumes its gradual slowdown. These glitches are thought to occur because the neutron star's interior contains a superfluid, a state of matter with zero viscosity that can flow without any resistance. This superfluid rotates faster than the star's crust, and occasionally, angular momentum transfers suddenly from the superfluid to the crust, causing the observable spin-up. Glitches provide rare windows into the exotic physics occurring inside neutron stars, where matter exists in states impossible to recreate in laboratories. Millisecond pulsars present a fascinating puzzle. These pulsars rotate hundreds of times per second, far faster than young pulsars, yet they're old neutron stars, billions of years old. How can an old pulsar be spinning so fast? The answer lies in a process called recycling. A millisecond pulsar was once a normal pulsar that slowed down over hundreds of millions of years. But if it's in a binary system with a companion star, and that companion evolves to become a giant star, matter can flow from the companion onto the neutron star. This infalling matter carries angular momentum, spinning up the neutron star like water hitting a water wheel. Over millions of years, the neutron star is spun up to millisecond periods, recycled into a new youth of rapid rotation. Some pulsars are part of binary systems where we can directly observe this process happening. X-ray binary pulsars show X-ray pulses as the neutron star accretes material from its companion. The infalling material, heated to millions of degrees before hitting the neutron star's surface, emits intense X-rays. These systems are the evolutionary precursors to millisecond pulsars, caught in the act of being spun up by accretion. The most rapidly rotating pulsars ever discovered are all millisecond pulsars, and some of them are in dense globular clusters where stars are packed closely together. The high stellar density in these clusters makes binary interactions more likely, creating environments where many neutron stars can be recycled through accretion. Some globular clusters contain dozens of millisecond pulsars, creating a cosmic percussion section where numerous neutron stars pulse at different rates, each one a precisely ticking clock, with its own unique period. Pulsars can also have planets. The first exoplanets ever discovered orbit a pulsar called PSRB 1257+12. These planets were detected through tiny variations in the pulsar's timing. As the planets orbit, their gravity tugs the pulsar slightly back and forth, causing the pulses to arrive slightly early or late in a periodic pattern. The planets orbiting this pulsar are thought to be second-generation worlds, formed from the debris of the supernova explosion that created the neutron star, or possibly from material that later fell back onto the system. These are harsh worlds, bathed in intense radiation from the pulsar, utterly unlike the planets orbiting normal stars. Binary pulsars, where two neutron stars orbit each other, provide extraordinary laboratories for testing general relativity. The orbital motion of such systems produces gravitational waves that carry away energy, causing the orbit to shrink over time. The rate of orbital decay matches Einstein's predictions with incredible precision. The first binary pulsar discovered, PSRB 1913+16, provided the first indirect evidence for gravitational waves. Decades before, gravitational wave detectors directly observed them from merging black holes and neutron stars. The regularity of pulsar timing has practical applications. Astronomers use networks of millisecond pulsars across the galaxy as a cosmic timing array, watching for tiny correlated deviations in their pulse arrival times that would indicate gravitational waves passing through the galaxy. These pulsar timing arrays are sensitive to gravitational waves with much longer wavelengths than ground-based detectors can observe, potentially detecting the gravitational wave background from supermassive black hole mergers throughout the universe. Pulsars also serve as natural laboratories for extreme physics. The conditions near their surfaces, intense magnetic fields, extreme gravity, densities exceeding that of atomic nuclei, cannot be reproduced on Earth. By observing pulsars across the electromagnetic spectrum and measuring their properties precisely, physicists learn about how matter behaves under conditions that push the boundaries of our physical theories, testing general relativity in strong gravitational fields and probing the equation of state of matter at nuclear densities. These spinning neutron stars, these cosmic lighthouses flashing their beams across the universe, represent one endpoint of stellar evolution. From the violent collapse of a massive star's core emerges an object so dense, so rapidly spinning, so strongly magnetized that it challenges our understanding of physics. Each pulse detected from a pulsar is a message from one of the universe's most extreme environments, a precisely timed signal carrying information about physics at the edge of what's possible, reminding us that the universe contains objects and phenomena far stranger than we could have imagined before we discovered these remarkable, spinning stellar remnants. The glowing clouds, where stars are born. Scattered throughout the galaxy are vast clouds of gas and dust, some spanning hundreds of light years across, glowing with ethereal colours against the darkness of space. These nebulae are the cosmic nurseries, where stars come into being, regions where the raw materials of the universe, hydrogen and helium from the Big Bang, mixed with heavier elements forged in previous generations of stars, gather, collapse, and ignite into new points of light. Understanding these stellar nurseries means understanding one of the most fundamental processes in the cosmos, the transformation of diffuse gas into concentrated spheres of nuclear fusion that will shine for millions or billions of years. The process begins with the molecular cloud, a region of space where gas has accumulated and cooled to temperatures only a few degrees above absolute zero. These clouds are dark when viewed in visible light because the dust mixed with the gas blocks starlight from behind, creating dark patches against the background glow of the Milky Way. But observe them in infrared or radio wavelengths, and they reveal intricate structures, filaments, cores, and clumps where the density varies, creating a complex web of material threaded throughout these regions. Molecular clouds are mostly hydrogen, but at the low temperatures found within them, individual hydrogen atoms have paired up to form molecular hydrogen, H2. This molecular form is more stable at cold temperatures, and these clouds also contain molecules that might seem surprising in the depths of space: carbon monoxide, water, ammonia, formaldehyde, and even more complex organic molecules. The chemistry occurring in these cold clouds is rich and varied, with molecules forming on the surfaces of dust grains and in the gas phase, building up a diverse molecular inventory over millions of years. Something must disturb these clouds to initiate star formation. A cloud can exist in a stable state for a long time, with internal pressure from the gas supporting it against its own gravity. But if the cloud is compressed, if its density increases beyond a critical threshold, gravity begins to win. This compression can come from several sources: a shockwave from a nearby supernova explosion pushing through space, the compression created when spiral arms of the galaxy pass through the region, or even the radiation and winds from existing massive stars that can trigger collapse in adjacent cloud material. Once collapse begins, the cloud fragments into smaller pieces. A single large molecular cloud doesn't collapse into one giant star. Instead, it breaks apart into hundreds or thousands of individual collapsing cores, each one potentially forming a star or a small system of stars. This fragmentation occurs because as the cloud collapses, it develops instabilities. Regions that are slightly denser collapse a bit faster, pulling in material from their surroundings, and these growing density enhancements become the seeds of individual stars. Picture one of these collapsing cores. Initially, it might be 1/10 of a light year across, containing perhaps a few times the mass of our Sun, with a density barely above that of the surrounding cloud. As it contracts under its own gravity, the material falls inward, but it doesn't fall uniformly. The core rotates slowly, inherited from the overall rotation of the cloud, and as it contracts, conservation of angular momentum causes it to spin faster, just as a figure skater spins faster when pulling their arms inward. This rotation prevents all the material from falling directly onto the forming star at the center. Instead, material settles into a rotating disk around the protostar, a flattened structure where gas and dust orbit the central condensation. This is a protoplanetary disk, the structure from which planets will eventually form. The material in this disk gradually spirals inward, losing angular momentum through viscosity and magnetic effects, feeding the growing protostar at the center, while the outer portions of the disk may remain in orbit for millions of years. As the protostar grows, accumulating more and more mass from the infalling material, its center heats up. Gravitational potential energy converts to thermal energy as material falls inward, and the temperature and pressure at the core climb steadily. The protostar begins to glow, first emitting infrared radiation, then gradually becoming brighter as it contracts. At this stage, it's not yet a true star. No nuclear fusion occurs at its core, but it's radiating energy produced by gravitational contraction, a process called Kelvin-Helmholtz contraction. The infalling material doesn't simply accumulate smoothly. Young protostars are violent, turbulent objects. They generate powerful magnetic fields that interact with the surrounding disk and the infalling gas. These magnetic fields can launch jets, narrow streams of gas that shoot outward from the poles of the protostar at speeds of hundreds of miles per second. These jets plow into the surrounding molecular cloud, creating bow shocks where they collide with the ambient gas, heating it and causing it to glow. These glowing regions, called Herbig-Haro objects, appear as bright knots and filaments near young stars, moving visibly over periods of years as the jets evolve and push through the surrounding gas. The jets serve an important function. They carry away angular momentum and energy, allowing material in the disk to continue falling onto the protostar. Without this mechanism to remove angular momentum, the disk would simply spin faster and faster, and accretion would halt. The protostar continues to accrete material and contract for hundreds of thousands to millions of years, depending on its mass. During this time, it's deeply embedded in the cloud that spawned it, hidden from view at visible wavelengths by the cocoon of gas and dust surrounding it. Infrared observations can penetrate this obscuration, revealing the glowing protostar and its disk within the dark cloud. These embedded protostars mark the earliest visible stages of star formation, objects that are still gaining mass and have not yet ignited nuclear fusion. Eventually, the temperature and pressure at the protostar's core reach a critical threshold, typically around 10 million degrees. At this point, protons begin to fuse, creating helium and releasing energy through nuclear fusion. The protostar becomes a true star, entering what's called the main sequence, where it will spend the majority of its life fusing hydrogen into helium. The energy released by fusion creates an outward pressure that finally halts the gravitational contraction, and the star settles into a stable configuration where gravity and pressure are balanced. When the star ignites, it begins to affect its surroundings dramatically. The radiation from the young star heats the surrounding gas and dust. Ultraviolet light from the star ionizes hydrogen atoms, stripping electrons away and creating a region of ionized gas called an H2 region. These ionized regions glow with a characteristic reddish-pink color, the result of electrons recombining with protons and cascading down through energy levels, emitting light at specific wavelengths. This is the glow we see in many famous nebulae: the Orion Nebula, the Eagle Nebula, the Lagoon Nebula, vast regions of ionized gas illuminated by the intense radiation from young hot stars. If the star is particularly massive and hot, more than about 8 times the Sun's mass, it produces copious ultraviolet radiation that can ionize gas over large volumes of space. A single massive star can create an H2 region spanning dozens of light years. Multiple massive stars forming in the same region create even larger ionized bubbles. The Orion Nebula, visible to the naked eye as a fuzzy patch in Orion's sword, glows because of a handful of massive young stars at its center, whose radiation ionizes the surrounding molecular cloud. The radiation pressure and stellar winds from young stars don't just make the cloud glow, they also begin to push the gas away, clearing out cavities in the molecular cloud. This feedback can actually trigger more star formation in the surrounding material. As the expanding HII region compresses gas at its edges, it can push that material above the density threshold needed for collapse, triggering new rounds of star formation in a process that propagates through the cloud. Young star clusters often show evidence of sequential star formation, with the oldest stars at the center surrounded by progressively younger stars farther out. The initial generation of stars alters the cloud, compressing and heating gas at the periphery, triggering the formation of the next generation. This process continues until the cloud is either dispersed entirely by the radiation and winds from the young stars, or exhausted of material dense enough to form new stars. The most massive stars, those dozens of times more massive than the Sun, live brief but spectacular lives. They burn through their nuclear fuel in just a few million years, and then explode as supernova, catastrophic events that briefly outshine entire galaxies. These explosions inject tremendous energy into the surrounding gas, heating it to millions of degrees, accelerating it to thousands of miles per second, and enriching it with heavy elements created in the star and in the supernova explosion itself: carbon, oxygen, silicon, iron, and even heavier elements like gold and uranium. These heavy elements mix into the molecular cloud, changing its composition. The next generation of stars that forms from this enriched material will contain more heavy elements than the previous generation. This process of stellar birth, life, death, and rebirth has been occurring for over 13 billion years, gradually enriching the interstellar medium with heavy elements. The earliest stars in the universe formed from nearly pure hydrogen and helium. Stars forming today, including our Sun, contain about 2% heavy elements by mass, a small fraction, but crucial for the formation of planets, and ultimately for the existence of life. The dust mixed throughout these star-forming clouds plays a crucial role beyond just blocking light. The tiny grains, typically less than a micrometer in size, serve as surfaces where molecules can form. Hydrogen atoms landing on a grain's surface can find each other and bond, forming molecular hydrogen far more efficiently than they could in the gas phase. Water molecules, carbon monoxide, and more complex organics also form on grain surfaces, then evaporate back into the gas or become incorporated into forming stars and planets. Star formation is not perfectly efficient. Only a small fraction of the gas in a molecular cloud, perhaps 1 to 10%, actually ends up in stars. The rest is either dispersed by stellar feedback, ejected by stellar winds and supernova explosions, or simply never reaches densities high enough to collapse. The molecular clouds we observe are continuously evolving, with some regions collapsing to form stars while other regions are being cleared out by the very stars that recently formed within them. Different regions of the galaxy have different rates of star formation. The spiral arms, where gas is compressed as it enters these density waves, show enhanced star formation, lighting up with the blue glow of young hot stars and the red emission from H2I regions. The galactic center, with its extreme environment and powerful tidal forces, has intense star formation, but also extreme feedback that can suppress star formation. The outer regions of the galaxy, with less gas available, form stars more slowly. Star formation is occurring right now throughout the Milky Way and throughout the universe. In distant galaxies, billions of light years away, we observe intense starbursts where entire regions of galaxies are forming stars at rates thousands of times higher than in our galaxy, triggered by galaxy collisions or mergers that compress enormous quantities of gas. The stars forming in those distant galaxies emit light that has travelled across most of the universe's history to reach our telescopes, showing us star formation as it occurred when the universe was much younger. The glowing nebulae we see in telescopes and photographs are not static monuments, but dynamic regions of ongoing transformation. The clouds are collapsing, the protostars are growing, the newly formed stars are dispersing the clouds that gave them birth. Within a few million years, the blink of an eye on cosmic timescales, a star-forming region transforms from a dark molecular cloud to a bright cluster of young stars, to a dispersed association of stars gradually spreading through the galaxy, each one carrying forward the legacy of its birth, enriching future generations of clouds with the elements created during its life, continuing the cycle of stellar birth and death that has shaped the galaxy since its formation billions of years ago. The crystal-like structures in space, deep within the cosmos, far from the warmth of any star, materials arrange themselves into patterns that would look familiar under a microscope on Earth. These crystalline structures form in the most unexpected places, defying the assumption that space is simply a chaotic void of random particles and radiation. In the cold depths between stars, water molecules slowly drift together, each one eventually finding its place in an organized lattice. The process happens atom by atom, molecule by molecule, as temperatures hover just a few degrees above absolute zero. Unlike the rapid freezing we experience on Earth, these ice crystals have time, millions of years sometimes, to achieve near-perfect geometric arrangements. The hexagonal patterns repeat endlessly, creating structures that catch and reflect starlight in particular ways that astronomers can detect from across the galaxy. Silicate minerals also crystallize in space, forming within the cooling outflows of dying stars. As a red giant sheds its outer layers, temperatures drop from thousands of degrees to just hundreds, creating conditions where molten rock can slowly solidify into crystals. These aren't the rough, irregular chunks we might expect. They're often perfectly formed olivine crystals, the same green mineral found in beach sand on Earth, but floating freely in the vacuum between worlds. Some of these crystals are microscopic, barely larger than the wavelength of light, while others grow to sizes that would be visible to the naked eye if you could somehow hold one. The environment around young stars presents another laboratory for crystal formation. In the swirling disk of gas and dust that will eventually become planets, temperatures vary dramatically with distance from the central star. There's a boundary, a line in space, where water transitions from gas to solid ice. Scientists call this the snow line or ice line, and it's here that water crystallizes directly from vapor without ever being liquid. The crystals that form are often elaborate, with branching structures that would rival any snowflake on Earth. These become the building blocks of comets and the icy cores of giant planets. Carbon takes on crystalline forms in space as well. In the hearts of ancient stars where pressures and temperatures reach extremes, carbon atoms arrange themselves into diamond structures. These aren't the large gemstones of jewelry stores, but microscopic grains that get expelled into space when the star dies. Scientists have found these pre-solar diamonds in meteorites that have fallen to Earth, tiny time capsules that formed before our solar system even existed. Each one contains isotope ratios that don't match anything that formed near our sun, proving they crystallized around entirely different stars. The surfaces of comets hide their own crystalline secrets. When these icy bodies spend long periods in the cold outer reaches of the solar system, the water ice in them gradually transitions from an amorphous glass-like state into a crystalline form. This transition releases trapped gases, sometimes causing the comet to briefly become more active, even when it's far from the sun. The crystalline ice has a different density than the amorphous ice, creating stresses within the comet's structure that can cause chunks to break away. Methane ice crystallizes on the surfaces of distant worlds, like Pluto and Neptune's moon Triton. At the frigid temperatures found in the outer solar system, methane behaves much like water ice does on Earth. It forms mountains and plains, fills craters, and even creates frost that glitters on the surface. The crystal structure of methane ice determines how it flows and breaks, shaping these distant landscapes in ways that mirror glacial processes on Earth, but with a completely different material. Salt crystals have been detected in the geysers of Saturn's moon Enceladus. Deep beneath this tiny world's icy crust lies an ocean of liquid water, kept warm by tidal heating from Saturn's gravity. When water from this ocean erupts through cracks in the ice, it immediately begins to freeze in the vacuum of space. But before it freezes completely, dissolved salts precipitate out, forming tiny crystalline particles that get ejected into space along with the ice. These salt crystals tell scientists about the chemistry of that hidden ocean. In the dusty clouds where stars form, silicate grains develop crystalline structures that affect how they interact with light and heat. When these grains are hit by shock waves from nearby stellar explosions, the intense but brief heating can transform their atomic structure, creating crystals with specific properties. The type of crystal that forms depends on the exact composition of the grain and the intensity of the heating event. Some become forsterite, a magnesium-rich crystal that glows warmly in infrared light. Others become enstatite, a pyroxene mineral with a different crystal lattice. The process of crystallization in space isn't always slow and gradual. Sometimes it happens in moments. When two white dwarf stars collide, the tremendous pressures and temperatures can cause carbon to crystallize almost instantaneously into diamond. The resulting object might have a core of crystallized carbon surrounded by layers of other materials, a cosmic gemstone larger than our Earth itself, hidden from view by its outer envelope. Amino acids, the building blocks of proteins, have been found in meteorites in crystalline forms. These organic crystals formed in the cold of space, where complex molecules could arrange themselves into ordered structures. The handedness of these crystals, whether they twist to the left or right, has implications for how life might have begun on Earth. The predominance of certain crystal orientations in space-formed amino acids might explain why life on Earth uses left-handed amino acids almost exclusively. Iron and nickel alloys crystallize in the cores of asteroids, forming structures called Widmanstätten patterns. These form when molten metal cools extraordinarily slowly over millions of years, allowing different crystal phases to separate and create geometric patterns. When metallic meteorites are cut, polished, and etched with acid, these patterns become visible as interlocking crystals that look almost like abstract art. The size and arrangement of these crystals tell scientists about the thermal history of the asteroid they came from. Sulfur compounds crystallize on the surface of Jupiter's moon, Io, the most volcanically active body in the solar system. The sulfur takes on different crystalline forms depending on temperature, creating a multicolored landscape of yellows, reds, oranges, and whites. Each color represents a different allotrope of sulfur, a different way the atoms can arrange themselves into crystal structures. These crystals don't last long in their original form. The intense radiation from Jupiter and the constant volcanic resurfacing mean that sulfur crystals are continually forming, breaking down, and reforming. In the coldest clouds of interstellar space, carbon dioxide freezes into dry ice crystals. These crystals coat the surfaces of dust grains, creating icy mantles that change how the grains interact with each other and with radiation. The crystal structure of this frozen carbon dioxide determines how easily it can trap other molecules, creating complex ices that contain dozens of different compounds, all organized in crystalline matrices. Phosphates and other minerals crystallize in meteorites under conditions that never occur on Earth today. These crystals preserve information about the early solar system, including the presence of water and the temperatures that existed on their parent asteroids. Some contain tiny pockets of liquid water trapped within the crystal structure, water that has been sealed away for over 4 billion years. The magnetic minerals in meteorites show evidence of crystallization in the presence of magnetic fields. The way iron oxide crystals align as they form reveals information about magnetic fields that existed around the young sun and in the interiors of molten asteroids. These crystals act as fossil compasses, recording ancient magnetic environments that have long since disappeared. Quartz crystals, so common on Earth, form in space as well, though through different processes. In the shocked material around impact sites, the intense pressure can cause silicon and oxygen to crystallize into quartz with unusual properties. Some of these crystals contain defects and inclusions that could never form under Earth's surface conditions, making them distinct markers of extraterrestrial origin. The study of crystalline structures in space reveals that the same fundamental physics that governs crystal formation in earthly laboratories operates throughout the universe. Temperature, pressure, chemical composition, and time determine what forms, but the basic rules remain constant whether the crystals form in a laboratory, deep in the Earth, or in the cold expanse between stars, where matter continues to organize itself into patterns of surprising complexity and beauty.